Our next presentation is from Matthew Rehrer at Harmonic. And he's going to be talking about shared storage optimized for media workflows. Matthew, please come to the stage. Thank you.
Yep. Thank you, Peter. By way of a quick introduction, this is actually my first time at this event, and I think everybody should be congratulated, not least of which Peter and Rick. This is a fantastic event, fantastic group, and I'm privileged to be here. I come from Harmonic. I come to Harmonic by way of Omnion, so if you smash the two together, I've been around for about 10 years with the company. Most of the time focused on storage, whether it be in the Spectrum server or indeed our Media Grid product line. But one of the best things about an event like this is that I get to come here and talk to you about technology instead of product pitch. So I'm actually going to go through a couple of things today. I'm going to talk a little bit about something that I refer to as wide area production, which is really much more of a workflow use case for storage and other associated bits and pieces. I'm also going to talk a little bit about the way that we've been thinking about solid state storage and the way that we've applied sort of a horses for courses approach to applying solid state to enterprise media storage. And then I'll wrap up with some interesting challenges that we see for the industry around solid state in particular. So starting off with wide area production, what do I mean by this? And really, what qualifies as wide? Well, I will stipulate that the Atlantic Ocean is wide. So if you look out the windows, in that direction and you try and get all the way across and try to sync up teams working on both sides of that body of water, that I will say that qualifies as wide. And we've spent some time working with one of our great customer partners working on some really interesting applications in this area. And we just got done recently with another one of these deployments where we were indeed crossing the Atlantic Ocean. People talked about network redundancy earlier, when Tim and John and Hugo were discussing their work, and redundancy is certainly important in this aspect as well. And so our customer actually deployed 2 independently routed 10 gig links to get a combined total when everything was up and running and happy of 20 gigabit across the ocean. And then what I'll go through is, what you get out of that kind of approach. But as we saw earlier, one of the things you get out of that approach is sometimes the best talent, the best people, the people that you want to apply are not in the location where the event is actually taking place. Much like Tim was on the other side of the Atlantic just a few minutes ago. The same thing happens with your production staff. And of course, content can be made portable, but people often cannot. So what does this look like? Well, if I hadn't mentioned it already, this was used in a sports highlights workflow. So I'm using the home and away terminology as sort of a subtle nod to that. So home was here in the United States where the vast majority of the production crew was, and it's a mixture really of the highly talented, highly skilled, highly prized people that also want to be able to tuck their kids into bed at night and don't want to be on the other side of the planet, as well as frankly, some of the less expensive talent. So people that are doing things like logging, where those people, the most expensive thing about moving them with a production is frankly the travel cost and the housing cost if you move people across a wide distance. So on bridging these two things, instead of the cloud icon, which I gather starts to get people's dander up, I have a big pipe, which I'm sure is a little bit more comfortable for everybody. So the big pipe between home and away is that 20 gig link that we used in this particular case. And on the away side, of course, that's where all of your feeds are. That's where all of the sports venues are. That's where all of the content comes from. And of course, you have too many of those things to just simply stuff them all through the pipe as full bitrate streams. So what do? We do, the ingest, the primary ingest, I should say, on-site locally, and then we have big pools of storage that we want to actually get our file-based workflow done on. And frankly, there are pieces of the file-based workflow that are happening on either side of the ocean, either side of the pipe. Of course, all of our high-res material doesn't just stay in the broadcast servers that are catching it. We want that all dumped to storage as quickly as possible so that all of the file-based tools can access those files while they're growing and do their work. We know that there's some things that we can stuff across this pipe relatively easily, and there's big value, like I said, in being able to do that logging activity on the other side of the ocean. So we're actually going to send absolutely all of the proxies across the pipe. So every ISO feed is available, and that's where that value add is being created on the home side in terms of logging and adding metadata so that the stuff becomes searchable and usable and makes the workflow much more effective. We want to be able to edit, and the best thing to do is to be able to get access to both the proxy material as well as the high-res material. And you can make decisions and shot selection based on low-res material, but when it all comes down to it, at some point you actually need to commit the edits. And in order to string that all together, you end up with a few more boxes being added to the system. So you'll notice that now we have media asset management on both sides of the ocean, so that we can actually put that metadata from the proxies into a system, and we can access the correlation between the low-res material and the high-res material and the metadata. And this allows the people that are sitting at the nonlinear editors and their producers to do shot selection and then only request the high-res material that's absolutely necessary for their projects. An interesting thing about this, some people just get this, and it's probably one of those things where, the younger you are, the more likely you are to just be comfortable with this new way of working with file-based workflows. But there was also an aspect in this project where the younger you are, the more inconsiderate you were likely to be. And so there were some instances where people put together a 10 or 11-hour EDL and said, I want this, I want this, and I want this, and they mashed the button and, of course, tried to suck all this across the pipe. So the moral of the story there is that if you give people tools, they will use them, and if there are rules that need to be made, you might want to make those rules clear up front. So not exactly a foolproof solution, but for shot selection and for, people that were narrowing down exactly what they needed for the highlights that they were able to put together, this system actually produced a highlights package in less time than the running time of the highlights package. So if I'm trying to put together a 2-minute reel, we were able to do that in a minute. So very impressive response time, especially for something that's spread over this kind of distance. And of course, at the end of the day, sports is often about the now, but it can be about the past as well. So there was a combination of the fresh material that's coming into the system as well as library material that was being added in for reference to past events. And then the bottom line is that all of the new material becomes historically significant as well. So there was a need ultimately, as the system is being torn down, to bring as much of the material across that 10 gig link so that it would in turn end up in the permanent archive for the next time that the production was used. So my personal style, I love to answer questions as we go. So if anybody has any questions on this topic, go ahead and deliver those now. But what makes this all work, of course, is you cannot fill this pipe without WAN acceleration. So we're talking many orders of magnitude speed up over traditional FTP when you're using something like Aspera or Signient. In this particular case, there was another vendor that we worked with named File Catalyst who did the WAN acceleration on this particular project, and they did a fantastic job. and really talking about multiple orders of magnitude in terms of the difference in speed delivering these files across such a large pipe. So if there aren't any questions at this time, one of the things, sure.
I'm not familiar with the term WAN acceleration.
Gotcha. So in a nutshell, WAN acceleration is a technology that helps to fill the full bandwidth of the pipe that you have available to. So when you go across a very long distance like this, you have very high latency, and with a protocol like TCP that makes sure that every packet gets there correctly, you end up with things like a TCP window size that will clamp down when latency increases. And what WAN acceleration does, different people implement it different ways, but it basically makes sure that you still have a non-lossy network, but it keeps the latency from packet send to packet receive from affecting the bandwidth of the pipe. So it's a way to fill the pipe. So great question. And one of the things you'll notice is that that pipe is not full, at least not in my diagram. So anybody think of anything else that you might want to stuff across this pipe when you have a production team on this side and a production and editorial team on the other side? Communications, exactly, and actually multiple kinds of communication. So this particular group did, they had a video conferencing link set up in both facilities, so anytime FaceTime was needed, they could actually sit down and literally look across the ocean and solve problems verbally face-to-face, the way that we all do a very good job of solving problems. And the other thing is they did all of their intercom communication. So you could literally be in a machine room and mash a button and speak into a mic to somebody else on the other end in another machine room. So very cool stuff with communication. And the other thing was there was some IP contribution as well. So you could bring across something like a clean feed that was compressed and fill some of the rest of this pipe. So very interesting project, and novel use of storage and some of these gifts from the IT world that Tim and John and Hugo were talking to us about earlier. Yes, Carl.
The MAMs that you described there as the one that's on the away side, a lightweight version of the more exotic one on the home side, or go through what's in the MAMs themselves?
It's a very good question. So that, once again, is not a component that came from Harmonic ourselves. In this case, this was Interplay from Avid that was the MAM. And it wasn't lightweight. I ran out of pixels on this diagram, so if I were to really portray this accurately, there's a whole bunch of other stuff here, including editorial on both sides of the ocean, and so you actually wanted the full heavyweight MAM on both sides of the ocean, and in fact, the pipe could be used bidirectionally. You might pull something from the archive across the ocean to the other side, just like you would pull the high-res in, but great question. So, I'm going to switch gears a little bit now and talk more about technology than workflow. And specifically, as I mentioned, our approach and our thoughts around how we're using solid-state storage inside of our own storage products. And we really address the space that I refer to as enterprise media storage. And since I'm making up terms, and you notice I've made up the wide area production thing, now I have to define these things that I make up. So enterprise storage, I'm going to say, is of a serious enough capacity that it's often the entire working library for the enterprise, for all of the file-based workflows that are going on in the facility. And because of that, it ends up sitting right at the heart of the facility. So it needs to be extremely reliable as a result, and it becomes very critical. Because it's right at the heart of the workflow and everything is using it, it actually has to satisfy all of the applications that want to touch it, otherwise it can't sit there. So it ends up, the performance of the system ends up being defined by the power users and the power applications in the facility. And then I mentioned reliability already, and often when people talk about storage and they talk about reliability, they end up getting caught into this cycle of, protecting data and being able to recover data. And that that's below table stakes at this point, especially if you're the heart of a file-based workflow. Instead of worrying about making sure that you're protecting data, what you really need to do is design a system that does not go down for hardware failures, does not go down for maintenance. And that's really sort of the crux of what I mean by enterprise media storage. So, how are we applying solid state in this? Well, typical use cases, we are, seeing majority people are using HD as far as new content that's arriving into a system like this. But we're still managing very large libraries of SD, and we're starting to see a lot more production done in 4K. And if you think back to what I was saying earlier about, the performance of the system being driven by the power users, the power-hungry applications, then it comes to be that at this point, 4K is really dominating the conversation about the performance levels that are needed in a system like this. And I talked about it being, the entire working library. You have to put some push pin in the board someplace with typical sizes. We do systems that are smaller than this. We do systems that are larger than this. But the vast majority of what I would class as the enterprise media storage is between 0.5 petabyte and 2 petabytes. So you're really talking about something that's far too large to be all flash today. And we can argue at the end of the presentation perhaps about the point at which we can go to all flash and what that will look like. But today we're not seeing people want to budget for what it would cost to do this kind of capacity completely as solid state. No doubt there are benefits performance, there are benefits reliability-wise, there are even TCO benefits in terms of power and cooling, but we're just not quite there yet. So how do we apply solid state in a really, horses for courses matter when you have a situation like this? So we actually took a what I would refer to as a layered approach. So I'm dividing up a file system into its component pieces, and these are not to scale for reasons that will become obvious in a moment, because obviously the vast majority of the content that's in your file system is in the data servers themselves. But in order to illustrate this, the metadata, what people think of as the inodes of the file system, the locking, the file names, the modification times, things like that, all live in metadata servers in a typical clustered file system. So you have things like the file system tree, all of the attributes of the files that I mentioned earlier, and then there's a translation layer where you need to connect those file objects to the actual bulk data that's stored in the data server. So once you do that, you cross this line where you get into the data servers themselves. You have further addressing in there, which is where do these chunks actually live and on which physical disks are they located? And at the bottom of the whole thing is all of the bulk data, all the stuff that you meant to store in the first place. So we took this and we divided it up into chunks. Like I said, you're talking about 0.5 petabyte to 2 petabytes. So here we're using disks, and by this I mean literal spinning disk, enterprise grade SAS SATA 7200 RPM drives, so the typical thing that we use in this area. But we're trying to satisfy all those demanding applications from a performance perspective. So we wanted to be able to use SSD in a few places to speed things up that would really pack the most punch. So solid state, I'm going to use somewhat liberally, and I'm even going to include things like DRAM. DRAM, of course, is not persistent, but while the system is up and running, we decided we could actually stuff all of the metadata for the file system into DRAM. So you never have to deal with the performance lag of seeking on a physical spinning disk in order to get to this stuff. This is the stuff that needs to be lickety-split fast so you can actually see what you want before you even start selecting stuff to move it across. We need that metadata to be persistent, though, of course, and for this job, everything that gets changed in that file system or added to the file system ultimately is committed as quickly as possible to non-volatile solid state storage. In this case, these are typical 2.5-inch drives when they're in the metadata servers. But you also see that these boxes overlap that bulk data section, and that is intentional. So both in the case of the DRAM and the solid state storage, we have some of each in the actual data servers as well. And the DRAM in the data servers gets used for read-ahead caching, write caching, and the non-volatile in the data servers is actually completely different from the 2.5-inch typical SSDs that we use in the metadata servers. In that case, we're using a different approach to solid state that I'll talk about in a second, that really delivers what we call our fast acknowledgement or fast ACK cache. So we can actually accept very small writes into the system. They're bulk data. These could be metadata files, caption files, things like that. And you want to be able to say, I have that, I have that, I have that, so that the application that's using the system can get on with its business. We do that by deploying non-volatile solid state in the data servers themselves. So we're doing several things here. So, some things have to be persistent in the file system, all of the metadata, all of the bulk data, and in that case, we have different horses for courses approaches to the persistent data. We also need to be able to be fast for several things, and this is where we're really deriving the benefit from solid state. So fast access to the metadata in the DRAM, the ability to commit those small files quickly, which go into the NVRAM and the data servers themselves, and then doing things like walking the entire file tree, which is something you would do, after a software upgrade of one of the nodes needs to come back up and synchronize its metadata with the other. That's a case where we want to be able to look at the persistent version of the metadata and match the two together, and that's where the solid state in the metadata servers really delivers its benefit, is to quickly get two different metadata servers back in sync with one another. And then, of course, there's the boilerplate reliability. And this is an interesting conversation that some of us were having on the side just before I got up here. And a lot of people are scared of the SSD boogeyman, the number of write cycles that SSD is rated for. And what has turned out to be the case is that you get an awful lot of benefit in terms of performance and also reliability from SSDs, and those ratings that people have been worried about, even in consumer level devices, and we have a bunch of those that we've been torture testing in labs for a couple of years, far outlive their rated lifetime. And the degradation that you see in a solid state device is actually very predictable. So instead of a mechanical drive that up and fails on you, of course, in the middle of the night on the weekend, as a complete surprise, what you get with the solid state device is quite literally a meter that you can watch tick down, and you can be very proactive about replacing that device before there is an actual failure in the device. So a lot of benefit in terms of the reliability in all parts of the system that we've been deploying solid state. So in terms of what we're doing today and what we're thinking about in the future, there are other places where we're using solid state that I haven't mentioned yet. All of the Linux OS images that are used in the system, for example, boot out of, today, enterprise-grade USB keychain drives, if you go ahead and believe that there's such a thing as an enterprise-grade keychain drive. We're really excited to move to some different technology there, either mSATA or M.2 is another thing that we're looking at that has a lot of flexibility there. I mentioned that proprietary or semi-proprietary non-volatile cache for the fast ACK in the data servers themselves. In this case today, we're using something that's known as NVRAM, which is basically a PCIe card with a big DIMM on it, a supercapacitor to provide power for that DIMM if the power for the system goes out, and then a smaller pool of solid state also on that same card that, while the supercapacitor still has charge, allows the DIMM to be emptied into the solid state storage for persistent storage. So that that allows us to say anything that lands in that pool is in fact persistent just when it hits the DIMM. In the future, what we think we're going to be using is a new technology known as NVDIMM, which basically collapses all of this functionality onto a standard DIMM that fits into a normal memory slot, and then newer motherboards now have power provisioning for a supercapacitor, also power provision for emptying that DIMM into persistent storage. And I mentioned earlier, today we're using 2.5-inch drives for the actual bulk metadata in the system, and that we don't see changing anytime soon. But another possible candidate here would be something that was, PCIe-based solid state instead of a commodity off-the-shelf 2.5-inch device. I mean, there are benefits to both. The nice thing about the 2.5-inch devices is, as we were talking about earlier, when you ride this IT curve, these commodity components actually reduce in cost, and that's something that we can always pass on, either in the form of higher capacities or lower costs for the same capacity, and it provides a nice unit of field replaceable component for something that we know is going to fail at some point in the future. As far as bulk data goes, I think that, like I said, I think eventually it will make sense to store all of the bulk data in the system in SSDs, and there are a lot of benefits in terms of power and reliability there, but we're just not quite there yet. And I mentioned that there were a few things I wanted to talk about that, I consider to be challenges for the industry, where we don't quite have the right answer yet, I would say, as a group. One of them, people have been talking about for a very long time, but I've yet to see a really perfect or really good system that works for everybody. The ability to tier multiple types of storage, multiple file systems, and of course you'd want to be, vendor agnostic if possible in doing this, because you don't want to be locked into buying one of each of these from one particular vendor. But the real magic will be in making sure that the right content gets to the right tier at the right time without the user having to manipulate it. And I want to be clear that I think that the perfect solution will have this, but I think it will also need manual intervention as well. So when people do want to proactively say, I know no application has touched this and nobody's been notified, but I'm going to move this from tape to spinning disk or from spinning disk to SSD proactively, you have to have both. Every workflow needs these, overrides for things of that nature. So whoever gets this right will, certainly give a great benefit to the industry and, hopefully reap useful rewards from it. The other one is another more, I would say, recent or novel idea that only makes sense now that we have different clients than we have in the past connected to systems like this. So now we have these edge clients that they themselves probably have very fast SSD cache in them, can be PCIe-based flash, not even the 2.5-inch solid-state drives that I was talking about earlier. And often people at those edge clients are working just in a confined area. They have made shot selections and they've pulled in their high-res, and it's just a small pool, relatively speaking, of content that they need access to for several hours at a time. So what can we do in order to get those people access to the whole library, but to cache just a little bit that they need for their project locally at their system? There's a tremendous benefit in perceived speed up from a system that can do this. So these are the two things that sort of keep me awake at night, as we're thinking about the best ways that we can help our customers out in the field. And that actually is all that I meant to cover, but I'm happy to answer questions if you have any. Please.
Do you see this technology being used in? Do you see this technology being used in content distribution or content delivery networks in the way you've talked about, or is it just pretty much editing type stuff?
I spend a lot of time thinking about production, and a lot of the stuff that I've been talking about is production. But in point of fact, this same system that I've been describing is also very frequently used as the backing store for multi-screen origin systems. So, not necessarily in the CDN and not necessarily in the cloud unless it's more likely to be a private cloud. But for many of our content producers, they're seeing a benefit of having a system like this where their production takes place, and as soon as those assets are ready to be published, they literally go back into the same giant pool of storage. So it's easier to administer, one big pool instead of lots of little puddles. And the origin services can actually, they rely on a lot of the same high performance, low latency needs, so they can actually pull out of this same pool.
Thank you.
Other questions?
I was wondering on the away, if that was a global production, like designed for multiple away locations, or was that a static?
So good question. So the question was, was the away side on that wide area production a mobile unit, or was it a different sort of production? So in this particular case, think many, many mobile units. So this was a very large production, sort of south of Eurasia, recently happened in the winter time frame. Yes?
When you talk about WAN acceleration, do you include things like increasing the data block size being transferred over to the network, which tends to, if you do that, that tends to have a more efficient throughput if your network is reliable enough? Does that include that?
Yeah, and actually WAN acceleration is not my personal area of expertise, but when I was talking earlier about the window size in the TCP protocol, that effectively, is a larger block size. So as I understand it, yes, that's the primary trick, is keeping the network sending those very large blocks, even though latency happens and even errors may happen. That's what causes TCP to clamp down that window size. When it starts to see errors, it says, hang on, I'm operating on a very high latency network. I don't want to be sending these huge blocks if I'm going to get little errors in the middle and have to retransmit a big chunk. I'm going to be smart and clamp it down to a very small block, and I'm going to wait until I get a response that says, yes, that was good. And so, a typical TCP network over this kind of distance will drip, drip, drip little bits. What you want to do is trick it into sending huge blocks and then fix them. You still have the reliability of TCP in terms of, there's zero error rate because you will retransmit stuff that has gone wrong, but you want to keep those blocks large. Yes?
What all the different LAN accelerating companies do, File Catalyst, Aspera, is instead of using TCP, which is what you'll get over FTP and stuff like that, they'll use a UDP packet because it has a much bigger payload and is connectionless and could care less where it's going. And then they use a back channel. It's essentially two streams. The UDP stream is for delivering the media, and then there's a back channel that says, hey, did you get that packet? No, let me resend it. Whereas in TCP, it's gonna, every time it sends a packet, it asks for an acknowledgement, and then it sends the next packet, which is why it slows down over large latency.
Great. Thank you for the education. That was beneficial to me, if not for everybody else. In the back, please.
You talked about using SSDs to improve access, write and read speeds. Can you talk briefly excuse me, on backplane and network connectivity regarding access speeds?
Yeah, in any system like this, you're really trying to balance a whole bunch of resources, and whatever the slowest element in the system is the thing that's going to define the performance of the system. So I mentioned that we're using for the bulk data today, and as far as I know, everybody else in the industry is using either SAS or SATA drives. We're coming up on a transition where we're going to get to 6 gig SAS. Today we're at 3 gig SAS. And that causes us to rethink all of the balancing choices that we've made today. So we've not really stranded performance anywhere in the system, balancing, the 3 gig SAS that we have, or sorry, the SAS that we have today versus the network. In this case, the front end connections to the system that I was describing is actually Ethernet, since that seems to be the theme of the day. We've started off with 1 gigabit Ethernet, and we're now at a point with 10 gigabit Ethernet where we talked about the sort of the IT industry, coming in and replacing technology that's been near and dear to us. In the storage industry, we see the same thing, and the IT industry eats its own. So we made, I think, a very wise choice a number of years ago not to implement this system based on fiber channel, but instead based on Ethernet. And that same diagram that John showed you with the people with the progressively larger arrows and pipes, you see Ethernet eclipsing fiber channel in the same way that Ethernet has eclipsed SDI. So we balance between the backplane in terms of the SAS fabric, the Ethernet fabric, and then the devices themselves, and try to come up with something that makes the most sense economically without stranding performance at any bottleneck in the system. Any other questions? Thank you very much.